Welcome everyone. This is the SNIA Ethernet Storage Forum, or ESF, webcast, File versus Block versus Object Storage. This is part 2, or the second webcast in our great debate series. And we hope you're looking forward to some content. We have a lot of great content and great presenters here for you today. In fact, our presenters are Mark Carlson, co-chair of the SNIA Technical Council and working for Toshiba, Saqib Jang from Chelsea Communications, and Alex McDonald, who is from NetApp, who is also SNIA ESF Vice Chair and an active participant in several other SNIA groups. I am John Kim, Chair of the SNIA Ethernet Storage Forum, and it's my pleasure today to bring you an interesting webcast debating file versus block versus object. Before we get started, a little background. SNIA is a very active organization in the storage industry. We have more than 170 leading industry organizations, nonprofits, universities, and vendors who are members, more than 2,500 individual contributing members as part of that, and more than 50,000 IT end users and storage pros worldwide. So you can learn more about SNIA at SNIA.org and more about our technical organizations and standards development at SNIA.org/technical. You can also follow us on Twitter at SNIA. A quick legal disclaimer. Keep in mind that the material in this presentation is copyrighted by SNIA unless otherwise noted. All member companies and individual members of SNIA may use this material in presentations or literature as long as they reproduce the slides without modification and acknowledge SNIA as the source of the material. This is a SNIA project, and none of the authors or presenters on here are attorneys, and nothing in this presentation is intended as legal advice. There are no warranties expressed or implied in this presentation, so use at your own risk. And now on to our actual presentation and the great debate. We're going to talk briefly about data access and how is it affected, how is your choice of block, file, and object affected by differences in the type of data, how you want to access it, share it, or what type of workloads you have. We will then go into specifics about block storage, file storage, and object storage, and then the actual debate portion. Which is better than the other? We'll have some challenge questions about them. So we'd like to make sure, by the way, that if you have any questions, you ask them online during the webcast, and as time allows, we will answer them during the webcast or at the end. These slides will be made available afterward, as well as a recording of the presentation. And any questions we don't answer in the webcast will be answered in a blog posted on the SNIA ESF website. So after that quick commercial announcement, back to the actual webcast. So one thing that affects your choice of block versus file versus object is how does your application or user want to access the data? Do they want to access it all at once or piece by piece? And if it's piece by piece, how big are those pieces and what types of pieces are they? Is the data access sequential or random? And does it tend to be, well, we'll get to the sharing part in a second. And is the data, what type of data is it? Is it a database? Are they text files? Is it video or audio or photos? Could it be virtual machines or containers? And then is the data static or fixed? Is the data written once and then never changed? Or is it modified all the time? And you tend to modify it at the whole group of data or little bits of the data, bits and bytes of the data at once. There's also a question of data sharing. Does the data need to be shared, and at what level are you sharing it? Is the sharing being done by the application or by the storage device? And when you talk about sharing, if other applications or servers need to share the data, are they just reading it, or are multiple servers or multiple users trying to write to the same data at the same time? And that can make a big difference in how you want to access it. And if you are sharing, is it narrow or broad? Narrow sharing could be just 2 servers in a cluster that are sharing the same database. Broad sharing could be 400,000 people across the world who are all trying to stream the same movie or download the same web page. So that certainly makes a difference. And then we have to ask about security and access control. Do you need security? What type of security do you need? And at what level are you applying it? Are you applying it to large groups of data at once? Or is it a more granular type of security that has to be applied to smaller pieces of the data, whether those be blocks, files, or objects? And finally, the type of storage can affect the choice of how you access it. So that could be the media, It could be the type of storage controller and how fast it is, and also how it's connected. Is this local storage or is it networked storage? Are you connected by fiber channel or Ethernet? Or are you using SAS or SATA or PCIe? So the connectivity can affect the types of access that you use or which access method is best. So having posed those questions and with that broad outline, we now want to go right into the start of the great debate, and we'll start with block storage and Saqib Jang. Saqib, please go ahead.
Thank you, John. As John mentioned, I'm with Chelsea Communications, and I'm going to take the next few minutes to present an overview of the applications and how block storage is organized and how it's used by applications. Block storage is ideal for performance-sensitive applications which require low latency access for reading and writing data to and from storage. It's used in a majority of Tier 1 enterprise workloads such as structured database applications for transaction processing and data warehousing applications. Another common example is block storage supporting virtual volumes for mission-critical applications running as virtual machines. Block storage also enables fast response time, scalability, and reliability for cloud applications which use server-side processing. In block storage, files are split and stored as evenly sized blocks of data. And each block is simply a series of zeros and ones with its own address, but with no additional metadata information to provide more context for what that block of data is. It is up to higher level applications and or file systems to keep track of data location, context, and meaning. And block storage can be directly accessed by the operating system as a mounted drive volume, which enables simplified reading and writing of files to it. In terms of how block storage is accessed, applications basically use block commands such as SCSI or NVMe commands to write block data to block storage. The data block is transmitted by hardware or software storage initiators, which we're going to discuss in more detail later on, to either locally connected direct attached storage or SAN-based centralized storage that is shared by multiple hosts. The storage controller receives the data block over DAS or SAN connections and writes the block to the storage device. For direct attached block storage, the most common interfaces are SATA, SAS, and the newer NVMe interface. The NVMe interface was developed specifically for supporting flash storage and has the highest performance, 16 gigabytes per second using PCIe 3.0 by 16, and is expected to scale to even higher performance when PCIe 4.0 gets deployed. For SAN-based access to centralized block storage, the network interface options are Ethernet, Fiber Channel, and InfiniBand, each of which can support up to 100 gigabits per second bandwidth for initiator and target connections. And regarding deployment scale, Ethernet block storage can be deployed across LANs and WANs. Fiber channel SANs can be bridged using a protocol called FCIP, while InfiniBand SANs are only used within data centers. Next, we look at the storage I/O path for two popular SAN block protocols or block SAN protocols. The first one is the broadly supported iSCSI. Support for iSCSI is prevalent among all of the major operating systems. And in the case of iSCSI, application servers such as database servers use the iSCSI software initiator or an iSCSI hardware offload initiator to access the storage target. Software initiators use the host network stack for network protocol processing. In the case of the hardware offload initiator, it bypasses the server network stack, and it also supports an RDMA capability for reading and writing data directly from and to application buffers. So both of these capabilities, protocol bypass and RDMA, enable the hardware offload initiator to support very low latencies and improve CPU utilization. iSCSI storage targets typically support tens to hundreds of initiators, and thus commonly use iSCSI offload. In the case of NVMe or Fabrics, only hardware initiators such as Ethernet RDMA NICs, fiber channel HPAs, and InfiniBand host channel adapters are used. There is no, the performance requirements of NVMe or Fabrics are such that only hardware initiators are optimum. As with iSCSI offload, NVMe or Fabrics hardware initiators support protocol bypass as well as support an RDMA capability. And the result is again a very low latency and improved CPU utilization. On the target side, as with the initiator side, NVMe or Fabrics target always support a hardware offload capability. Moving to security, both iSCSI and NVMe or fiber channel protocol, SANs are targeted at enterprise applications, and thus both support a range of security capabilities. In the iSCSI case, authentication is available through the popular CHAP method, while fiber channel uses worldwide names to control access to storage by hosts. Both protocols support secure communication channels using encryption for data in transit. Ethernet networks allow LAN-SAN convergence while still maintaining security through logical isolation of storage and data traffic using VLANs. But fiber channel SANs are always physically isolated from local area networks. And lastly, for a review of how best to manage block storage, the SNIA Swordfish protocol specification has the goal of simplifying the provisioning, monitoring, and management of block as well as file and object storage. The Swordfish API can associate different classes of service and block storage of varying performance levels. An IT administrator would need only to specify the class of service to allocate storage to servers and virtual machines, rather than having to specify details on the block storage array. Capabilities include the storage provisioning with class of service, as well as replication and capacity and health metrics. So that's it for an overview of block storage, and I will turn it over now to John.
Thank you, Saqib. So we're about to go into file storage with Alex, but there are two questions that have been submitted. I want to answer one right now, and we'll hold the other one until the end. The question is, Fiber Channel uses SCSI protocol, which is correct. Does NVMe over Fiber Channel use SCSI? And the answer is no, NVMe over Fiber Channel does not use the SCSI protocol. It runs the NVMe protocol over a Fiber Channel transport, where regular Fiber Channel runs SCSI on top of the Fiber Channel transport. So hopefully that answers the question. And that said, Saqib, thank you. Alex, please go ahead with file storage.
Thank you, John. And good morning, good afternoon, good evening to everybody out there. Just a real quick technology point. The guys know on the call today that I'm actually doing this using my car as a Wi-Fi hotspot. The technology that we have available at our fingertips is truly amazing. Anyway, just thought you might like to know. This comes from my car. So, file storage. Let's talk a little about the history. The history of file storage is actually based on the history, I suspect, of systems like Unix that involved the idea of streams of data, not random access devices, but streams in the sense of things like paper tape and physical, magnetic tape. And file systems came about as almost filing cabinets for paper-based documents. So if you think about a traditional filing cabinet with paper-based documents in folders, well, there you've got the idea basically of what most modern file systems look like. They're a similar construct. They are collections of documents. They tend to be unstructured or structured data. It doesn't matter which. As we'll see, there's a wide variety of ways of connecting up these different types of documents and providing an overall structure to the thing that I'll demonstrate in a second. So the use cases for file storage are things like sharing documents, clustered databases, big data, using for files like video and audio for media and entertainment, for technical computing or HPC where you're dealing with very large data sets, for instance of genomic data. And they're the foundation for application independence because there's a consistent set of APIs you can use that deal with all file systems. And I'll cover that in a sec. But the idea that file systems are only for things like, I don't know, PDFs or text files or, executables or whatever it might be is not the case. There's a wide variety. The one great thing about file systems, as I'll explain in a second, is they're all things to all men, all women. So the characteristic of a file is that a file has a name. It's got some kind of name that we associate with it, and is byte addressable. Now that byte addressability is really important. So Keeb's already talked about block storage. Block storage is block addressable. File storage is byte addressable. We can address down to the individual byte, and we can read and write various parts randomly in that file. And this name is really just the thing that we use to initially identify the file. We then associate that name with a handle, and all the I/O operations are done through this file handle. And that gives us great application independence. Those files are organized in the named directories, which is, the directory itself is actually a structured file. So you've got files, if you like, living inside files. And there are several effective layers in terms of file storage, but they may be blended. So there are three primary parts. The first three are the logical, virtual, and physical file systems, and I'll talk about those in a second. And then a network access layer that allows you to get access to this lot over the top. On the right-hand side, I've just got a couple of diagrams. One shows you that tree structure of directories, which are files, that contain other files. And on the farthest right, there's a simple example of opening a file and reading and writing to a new file and then closing that file. And that's simply a file copy operation. But it just shows you the flexibility. That file copy operation can operate on any file, on any technology, as long as it appears inside our file structure. So immense flexibility with file systems. So in terms of the application view, there are POSIX, which is a standard that was developed years ago, or close to POSIX-like support in all the major OSs for file systems. And the primary operations are things like opening a file, closing a file. That's associating the handle with the name, reading, writing, and updating that file. and creating, renaming, deleting files. So you've got a full set of operations there that allow you to deal with files, regardless, as I say, of where they live, and I'll explain that in a second. This same set of calls allows source code portability. I can write a small C application, for instance, that runs on both Android, on Linux, on Windows, and have it completely independent of the underlying technologies that I'm using because of POSIX and that independence that it provides. So the applications can treat files as a stream, a set of bytes that starts at byte 0 and goes up, or objects, or unstructured data, or structured data, or a block. Why can't we actually define block files over the top of a file system? You know, we can have blocks. We can have 256-byte blocks. I mean, the whole point about a file system is, although it's byte addressable, that doesn't mean to say you have to address it in bytes. You can address it in blocks if you wish to. So it's incredibly flexible in terms of the way that you can organize the underlying storage. So a file system starts off with where Saqib came in. It's a physical layer built on top of storage devices. And those storage devices are typically nowadays disk or flash, or persistent memory if we're looking at some modern memory technologies, or old-fashioned technologies like tape or paper tape or whatever it might be, you know, terminal input. So we've got a physical layer built on top of the storage device. We then build a virtual layer on top of that physical device. So let's say our physical device is one of Saqib's block devices. We then build this virtual layer using a file system like, let's say, ext4, which is ext4, which is a Unix file system or a Linux file system. And there are literally hundreds of these different types of file systems with different types of characteristics. Some of them are more suited for disk devices. Others are more suited to flash. Some of them are log-structured file systems. Some of them do checkpointing. So there's a variety of file systems for different use cases, and each has different characteristics. But this particular virtual piece becomes the mount point or the share that we use to insert into this directory structure on the right-hand side. So you can see various mount points there. If you expand the screen a little, you'll see they've actually got names associated with them. But each of those can be a mount point, and we can have a different file system under each mount point, but it simply looks like a single organized structure from a root. The root in this case is the one right up top, the slash. And that logical layer brings together all these virtual levels into this single root, a tree of directories and files, and names and paths. The path is simply a set of names that allow us to walk our way through a file system to get to the individual file we want. Do we care where that file is located? No. Do we care what kind of storage that file sits on? No. Why? Because we can use those POSIX compliant open and close, read, write, and update, create, rename, and delete operations on all of those files within that directory structure, regardless of what the underlying technology is. So if that's the file system, how do we get access to it? Well, we've got a distributed file system that we can use. I beg your pardon, I've just gone forward 1, 2 slide too many. I beg your pardon, take it back. We've got a distributed file system using, and typically it's either NFS for Unix and Linux type systems, or SMB for Windows systems. And those are the predominant file access methods to get access to these directory structures over the network. And they provide things like, for instance, sharing and locking, so I can actually share files. I can lock various parts of files or whole files. And effectively, they provide a transparent layer over the top of all these file systems and the communication layer so that I can go out there and read and write and update, etc. That communication layer is almost always Ethernet and TCP/IP. That's the commonest way of accessing these file systems. So in contrast with the underlying block storage that might be using fiber channel, it might be using SCSI, it might be using, there's a variety of techniques we can use underneath. At the top level, our network file system doesn't really care. It's just Ethernet and TCP/IP over the top of it. And there's no knowledge required by the application of any underlying structures, and nothing pokes through to the end user. He doesn't see any of this underlying technology. So in terms of the performance of file systems can be very good indeed, actually, and it generally competes with things like SCSI, and it's suitable things like, give you a couple of examples there, VM data stores. A lot of people put them on SANs, but you can put them on NFS as well. Containers, and also things that help with providing high performance are parallelization. For instance, in the NFS world, we've got parallel NFS, little diagram at the bottom right, which shows you that we can actually spread an individual file across multiple devices and access it in parallel, so that we've actually got quite a bit of improvement of performance because we're multiplying up on the bandwidth we're able to get to those devices and reducing correspondingly the latency. However, the abstraction in a file system is deeper. I mean, we've got the file system sitting on top of the underlying, we've got this logical, virtual, and physical layers, and then the network layer, and the abstraction, the whole abstraction of that storage is much deeper. Hence, the latencies tend to be higher than block, and that can be a downside sometimes, where you might want to consider a SAN instead of using file systems. Have there are other advantages, like space requirements can be significantly less. We can compress files. We can hole punch them. We can have things called sparse files. Perhaps I've got a file that consists mainly of lots of binary zeros. Well, why am I storing them? If I only have a block, let's say, of data for the first megabyte and then a block at the 10th megabyte, then the bits in between don't need to be stored, and I can punch out those holes and save on the underlying storage. Even though the file looks a lot bigger, it might be hole punched and compressed, and that's a real big advantage to file systems. In terms of security and privacy, it's pretty good. NFS and SMB use Kerberos or LDAP, which are flavors of the same thing, which are basically systems that allow you to authenticate and authorize. And authentication, and the two things are different, but authentication is about proving to the system that you are who you claim to be, and then authorization is what you're allowed to do once you actually get in, what groups you're a member of, what access control. And both NFS and SMB use ACLs, or access control lists, to actually manage the underlying security of the files that they're providing you. In terms of management, goodness, where do we start? File storage has a huge amount of management utilities. It's got some metadata, it's got more than blocks, it's got a lot less than object. So it's got things like attributes and extended attributes, and the primary ones of those are things like times and dates of when the file was created, when it was accessed, when it was updated, and its size is a good piece of metadata. But there are many thousands of utilities that provide you with archival, backup, restore, things like NDMP, for instance, compression, deduplication. There are specific structured file type management technologies, for instance, for things like videos or for sound or for specific types of document like PDFs. So there's a huge amount of ways of managing file storage and managing the things that those files represent. And in fact, it's one of the best ecosystems I can think of in terms of its, if you like, capabilities and its breadth. So back to John.
Alex, thank you very much. Before we go on to Mark and object storage, I'd like to answer one question that came in from the audience. Yep. And the question is, I get confused when someone says block size for block storage, because don't we also talk about block size for NFS or file storage as well, and maybe even for object storage? So can you explain the difference between saying block for block access versus file access, and block size, which is a term that we use even when we're talking about file storage?
So really, the idea between the block size and file storage is pretty irrelevant, actually. It's just simply a way of expressing the size of the thing and the way that it might be managed in terms of the underlying unit. We're not really interested in an NFS or an SMB system in blocks at all. And in fact, if we want to think in terms of blocks, we can impose our own block structure over the top of the data, regardless of the underlying storage. So no, we don't tend to think in terms of blocks when it comes to file systems. And I suspect Mark will confirm that we don't tend to think of it at all when it comes to object systems. They're completely, if you like, blockless.
Okay, very good, Alex. And we may come back to that afterward. But for now, let's move on to Mark Carlson and talk about object storage. Mark?
Thanks, John. Yeah, so object use cases, if you will, mainly around public, private, and hybrid cloud storage. The ultimate app looks like something like a sync and share. So you can see your files from your desktop or your device. You can offload attachments from email and store them in the cloud and reference them instead of send them all by value. Archival storage is a big use case. The ultimate tier in many cases is an object repository, whether in the cloud or on premises. Serverless container storage, when you're developing microservices and hosting them in containers. Object storage makes a lot of sense because it's already a shared storage environment. Analytics and Internet of Things, machine or deep learning, use object storage to sort of ingest the data from the edge, dump it in a lake of data, if you will, analyze the data, train neural networks, and then make decisions with those neural networks. And of course, big use case is greenfield applications. Legacy applications are typically written to an object interface, but greenfield applications can be, and more are being developed over the years. So how is data organized for objects? Well, objects have a handle, and that handle can be a URL, or it can be an object ID, or it can be both. You don't create a handle by mounting anything. It's just an intrinsic part of the object. Objects can be grouped into flat buckets, or they can be in hierarchical containers, also with URLs as well. And the most important thing about objects is they have metadata. And that metadata can be either user metadata, which is generated by the application, or it can be system metadata that is determined by the system and interpreted by the system. And then objects can have versions. In fact, the underlying storage might be immutable in the case where a lot of hyperscalers, for example, only have an immutable storage layer underneath. They don't overwrite objects. They just create a new version of an object. And then the storage of objects may actually be RAIDless, right? Alex was talking about the parallel file system. That's pretty much what every object storage system does, is it splits the data up into smaller pieces, applies erasure coding parity, if you will, and then distribute those shards into multiple different storage devices. As I mentioned, there's no need to mount an object access method like there is in block storage or file storage. You can basically access any object from any endpoint as long as you have the right security, like Alex said, authorization and authentication. And then from that URL, you resolve the actual location of the data. And what I mean by that is you could have a load balancer in front of a bunch of these object systems, and it resolves that URL to a specific system that has your data and can respond to your request. And when you put your objects into the storage system, it can transparently move your data back and forth between private and public infrastructure, maybe to different kinds of storage devices with different characteristics as far as latency and bandwidth and so forth. And over time, your object might migrate from a very fast local repository off into a cloud that takes much longer to respond to requests. And then an object store can sit on top of a file system, or it can sit on top of block devices, or it can sit on top of KeyValue devices, for example. Speaking of KeyValue, a lot of applications think in terms of accessing a key with its associated value. So they store their data using a key and using a value, and they expect to get their value back by specifying the key. RocksDB is a very popular one. There's multiple of these key value databases, if you will. But also there's work that's been started on creating a new key value interface for the actual drives. And so instead of using a block device underneath the object store, it would be based on a key value. And that's when you can take the object ID, let's say, or maybe a hash of the value perhaps, and use that as the key for the shards that you're going to distribute across multiple devices. And so this ends up being less costly and more efficient for things like PCI SSDs, and really reduces the CPU overhead on serving that data up to the eventual end user. So performance and, of course, availability of objects is at scale. And I really want to emphasize this because it's when you have a huge storage system that objects start to make sense for you. It allows you to do scale-out implementations. And those implementations might have multiple copies of the data in that. And when you have multiple copies, you can actually serve up the copy that's going to be the quickest. Even when you shard it and send it across, multiple drives, you don't need a response from all of the drives, just some core quorum of drives to respond in order to create the eventual object back to the user. So that's been used to speed things up as well. And then having these globally unique handles allows you to respond from the least loaded node through these load balancers. However, it may not be the highest throughput or lowest latency for an application that's running on a single machine with attached drives. Maybe you should use block for that, or maybe you should use a local file system for that. So how do you use objects? Well, you access them via standard internet networking infrastructure. So that includes the name service, hypertext transport protocol, TCP/IP, Ethernet. It doesn't require converged Ethernet like a lot of storage protocols do. It can work over the internet, basically. There's broad support from nearly any programming environment for object access. So whatever application programming language you're using, there's probably support already built in for object access. And just using objects overall is more intuitive to the person that's storing data in an object store, right? Your browser can be used when you pull up a cloud object store. In your browser is a listing of all the objects. You can click on any object. Your browser will show it to you. There's no need to load a specific app. There's no need to mount a specific file system. There's no need to format your data into blocks. You can access it byte by byte, or object by object, or container by container of objects. So all that is available to you. And then security and privacy. Rich object metadata can be used to provide additional service levels. You basically tag your object with this metadata. It can tell you who has access to your objects. You can share objects with only the people that you choose to. You can authenticate and authorize just by the fact that you have the URL. Although that is not recommended as a security mechanism. But you can actually include credentials with an object access so that only that person who knows that password could access the object. You could grant temporary access. Give them access for a day and then automatically revoke it. If they don't download it in the first day, You remove access to it, maybe even delete the file, save some money. Audit trails. Audit trails are very important to help both after an intrusion and to monitor real time what's happening with your data. And then the management of your data in the cloud can be interoperable and enhanced because you can actually mark on each object what are its requirements at this point in its life cycle. Does it need to be very close? Does the latency need to be very quick? Does the bandwidth need to be very large at this point in its life cycle? Maybe later the bandwidth doesn't need to be so great and the latency doesn't need to be so quick. That can be done, and you can manage the treatment of your objects over time with interoperable metadata. And then the privacy of individual objects can be defined by the owner who has access. Maybe you have a medical file. You could grant temporary time-based access to your doctor, but still keep control over your medical data and keep it private from everybody else. So once you put your data into an object, how do you manage it? Well, as I mentioned, the metadata essentially are knobs that control the underlying data services and how they treat that object. And we call that data system metadata because it's a data service that's being used for that object to back it up, to move it amongst hierarchies, to protect it, to keep it from being deleted for legal reasons perhaps. And that knob basically controls how performant it is, latency, bandwidth, how available it is, how many copies, how far distance from each other, how protected it is, how often is it backed up, how much is it backed up, how long does it take to restore. And so these SREs, which is site reliability engineers at hyperscalers, storage administrators can use those knobs, they can automate those knobs, and then they can optimize the treatment of this data at this point in its life cycle, saving money on older objects by moving them off onto cheaper storage, for example. So, back to you, John.
Thank you very much, Mark. Before we jump into the debate, I did have one question about the object storage. So when people talk about object storage systems, I often hear the terms S3 and Swift. And I was wondering, are those APIs or are they KeyValue Access methods? In the context of your presentation, what are S3 and Swift in terms of accessing object storage?
Yeah, thanks, John. That's a good point. So there's various sort of interfaces that use the underlying HTTP protocol to move your data around. S3 is a interface to the Amazon Storage Cloud. S3 stands for Simple Storage Service. Of course, they layered on many other storage services over that simplified storage service. And every one of those new services has its own API. And these APIs are proprietary to Amazon. However, many vendors have reverse engineered the S3 API and support it on their own products. So S3 ends up being somewhat of a de facto standard for object storage. Swift is a project within the OpenStack community, and it is software that is an object store that you can pick up and deploy in your own environment, if you like, for private or hybrid cloud usage. And the Swift API, similar to the S3 API, allows you to create and delete, list, and whatnot objects that are in the Swift object store. And there's a third interface, it's not open source, but we do have an open source reference implementation for it, and that's called CDMI, or Cloud Data Management Interface. All three of these interfaces basically rely upon the underlying HTTP standard to do all the movement of the data. So you do an HTTP put to send an object into the cloud, You do an HTTP GET to get an object out of the cloud. This is the same across all three interfaces that I mentioned. Where they differ is in things like metadata, authentication and authorization, and so forth. But all the basic APIs use the same HTTP commands that are standardized by the IETF.
Got it, Mark. Okay, great. Thank you. So let's dive right into a compare and contrast and see how many questions we can get through and have a debate about which is the best way to access my storage and when should I use block, file, or object. So I'll start out with the first question, and this is to Alex and Saqib. Do databases prefer block or file storage, or can they use both? And why is one better than the other? Alex, why don't you go first?
So I like to think of the answer to this question a bit like a Venn diagram with overlapping circles. And there are strong cases to be made for having databases that are actually based on file storage. And some of those are to do with size, relatively small size, relatively low requirements in terms of performance. Or perhaps there are other reasons, perhaps distributed type databases where file systems are better able to knit together all the parts of a distributed database. Block storage, on the other hand, I see as being, out the other end of the spectrum. But somewhere in the middle, there's a really good question that no one can answer for you until you've actually tried it yourself. Do databases prefer block or file? Who knows in the middle? But there are definite, if you like, reasons for file at the one end of the spectrum and block at the other. But as I say, it's a bit of a Venn diagram, this one.
Saqib, any thoughts you want to add on databases?
Yeah, so I completely agree with Alex. There are a range of different applications and database applications, and each and block and file both have a fit. There's a particular type application that has a very good fit with block storage, and that is enterprise class OLTP applications, which require very fast access to storage, a lot of reading and writing of data, shared storage, as well as the sharing is supported within the upper level application. So those attributes make online transaction processing applications a very good fit for block storage.
Excellent. Thank you, Saqib. So OLTP would probably go on block. Distributed database would probably go on file, but then, as Alex said, there's a range of databases where in the Venn diagram that might go on block or might go on file, and that maybe the testing may be required to figure that out. What about for video storage? Let's start with Mark. Mark, should video storage always be object, or are there some cases where it's better off on object and others where it's better off on file?
So even with file content type of video, there may be several different access methods. For example, you might be editing a video file. Well, when you're editing a video file, you want to go sort of frame by frame through the video and make modifications. And when you're editing a video file, you don't want him to drop frames, for example, because you're trying to edit it. However, when you're playing the video file, you want it to play more or less in real time without any, hiccups in the middle. So when you're playing a video file, it's perfectly all right to drop a frame if you can't get it there in time. And the video playback software will extrapolate over that missed frame and seamlessly present the video to the user. So remember what I said about object being at scale where the performance and availability is available to you. If you plan to distribute your video to tens, hundreds, even millions of people, and you expect it to be popular, you're going to want something that can scale out to that kind of simultaneous access. And currently, object is the only way to go for that particular purpose.
All right, Mark, that's great. So if I'm actually editing the video or processing it, then I might want file or even block storage. But if I'm going to share it with millions of fans across the world, then object storage is probably the best way to scale out that access.
Yep. Yep.
Okay. All right, let's move on to the next one, VMs, virtual machines, and containers. Let's start with Saqib. Is block storage always the best way to store VMs and containers, or are there cases where sometimes it should be block and sometimes it should be file?
Block has a good fit with as being a storage option for VM and container environments. All of the main VM vendors have support for block storage, for example, SCSI and Fibre Channel in their hypervisors. And another good capability that block storage offers is it enables sharing across a range of hosts. And my belief is that depending on the performance and depending on how frequently data is changing, file storage can also be used for VM environments. And it'd be great to hear Alex's thoughts on that.
Alex, if you could go ahead. Oh, yeah, Alex, please go ahead.
Yeah, I was just going to say, I think the big thing here is scale. So, if I'm managing hundreds to thousands of VMs, I think block storage might be fine. If I'm managing tens to hundreds of thousands, then I'm going to be wanting a different solution. It's just too difficult to manage otherwise. And one of the advantages of file storage, and I suspect object storage as well, is that managing things at scale becomes a lot easier. If you've got a directory structure, for instance, or a hierarchy of VMs in various states of play, in various states of maintenance, in production, in test, in whatever they might be, whatever state they're in, that and the advantage of file systems and the utilities and the manageability of file system, I think, is a big argument to say, don't use block, use file, because there's an awful lot more management that you can do. And I suspect Mark might agree with me that getting out to real scale, hyper scale, then you probably want to manage these things as objects, because ultimately when you're getting out of that level, these are they're almost disposable, these things. I mean, if you've got millions of VMs, then I suspect you're running clones and copies and et cetera, of these virtual machines, where object storage is probably far more relevant than even file systems. But I think a lot of it's to do with scale and manageability, which you choose. Block, I'd say, yeah, great, up to thousands. File systems, beyond that, and object probably beyond that again.
Okay.
Yeah, it's
Alex,
really a matter of sharing your data between applications that are running there. If your application that's running in a VM doesn't need to share data with other applications running in VMs, then yeah, local file, local block is probably the way to go. If you do need to share between VMs, between containers, you want to have a protocol that allows you not to think in terms of, well, this is my copy versus his copy. It's all a shared copy, and you want something that can be accessed from any machine anywhere in the network.
Mark, thank you. Alex, thank you as well. Let me go ahead, and in the interest of time, we're running a bit short. Let me move to the next slide, and let's talk about performance. So let's go to Alex. Comparing block file and object, is one inherently faster than another? And does it always matter? Are there cases where maybe one's a little faster, but they're all fast enough?
So I'm going to take two very quickly, two case studies here. The first is performance in terms of a raw file system sitting on disk. Then I suspect that a file system is going to lose out because the stack is deeper. So let's take a fast SSD, for instance. The stack is deeper. You've got more software to go through to get to your data. And we're also dealing with the data not in structures that the SSD understand. We're not dealing in blocks anymore. We're dealing in bytes. And that really isn't there's a bit of an impedance mismatch. But there's a new class of memory coming along called persistent memory, where treating persistent memory like a block device is actually incredibly wasteful, because persistent memory is, as its name suggests, memory. It's actually byte addressable. And for that, file systems is the best way to do it. And building a file system over persistent memory is the way to go. And that is going to give you huge speed advantages because of the underlying memory technology. The file system will become a relatively thin layer over the top of that. So I think there are two ways of looking at this. One, what is the underlying substrate in which you're building the file system? And two, what does the file system buy you in terms of byte addressable, loads and stores rather than having to deal with blocks of data and doing IOs?
Okay, Alex, great perspective. The next question, Mark, can any type of storage access method, block, file, and object use flash storage? The reason I traditionally think of flash storage as being block and object storage as being hard drives, but is that just a stereotype that's not actually true?
Well, there are implications with solid-state drives on how much CPU do you have to put in front of them to make them useful, performant, etc., right? And amongst these, if it's a block-based SSD, that's absolutely the lowest amount of CPU overhead that you would need to serve it up as something like iSCSI or just over PCIe. File adds a little bit of CPU overhead. You have to worry about metadata now and hierarchies and superblocks and so forth. Object has, I would say, the most overhead when using flash storage. So to create an overall storage system, you're going to buy more CPU with flash storage than you would with the other access methods.
Okay, but you mentioned the KeyValue SSD. So if you have that, then those would be SSDs that sort of speak object storage natively. Is that right?
Yeah, it's kind of an object storage. It's a more efficient, CPU-wise, more efficient way to take SSD data and put it into objects that the end user actually wants. So you basically take your object, you shard it. Each one is a key value in a different drive, and coming back out of the drives, it's very easy to marshal those into a network using RDMA or DMA and send it out as a packet over HTTP. So it's very well matched, and it significantly reduces the CPU overhead of conveying flash-based storage into an object.
Got it. Okay. So I think for these next two questions on the slide, Saqib already talked a little bit about the third one, and Mark, you already talked about that at scale when it's distributed. You and Alex mentioned that in some cases a file system or object storage could have greater performance than block storage, especially if you have a broad distributed access. So let's talk a little bit about manageability. So let's actually start with the metadata question. So this will be for Mark and Alex. Who has better metadata? Does object or file have better metadata, or is it just different metadata? Alex, why don't you start?
The metadata that's in block storage is typically just protection metadata. It might be a CRC or a hash of the actual data, and that's used sort of end-to-end to make sure that the data you put on the drive is the same data you get back from the drive. Whereas file and object metadata are truly data about the data and can include not just the storage system metadata, which is who created it, when did they last access, who's allowed to use it, but also things like how performant and available and protected it is.
I'd also point out that metadata in the file system is not necessarily treated in the same way that the file system is. So you often find that dealing with metadata on a file is a lot less performant than dealing with the file. The file might be split across multiple volumes. You might be dealing with it in a performance way or a performant way, but the metadata tends to be held in the directory, and the directory tends to be a single object and tends to be a bit of a bottleneck. So if you're really looking to manage metadata or use metadata, then object's the way to go, because file has it, but it's more of an afterthought than it is actually a core feature of the storage solution.
If I could just interject for a second. Yeah, the focus as we discussed, block storage is on performance. So because that reason, the metadata function has to be supported or is typically supported by the upper level application that uses block storage. So the combination of those two factors enables block storage to provide low latency access to storage. So I just want to pass on that.
Okay, thanks, Saqib. By the way, we have about 6 great questions here, 6 or 7 unanswered great questions, and we will not have time to get to all those, so we will answer them in a blog that will be posted about a week after this webcast. So for all those you put in your questions, if we don't get to them, we will answer them online as well. So let's talk a little bit about security and sharing, and specifically about, well, sort of answering both. Alex, can we start with you? Is between file and object, do they allow any security or sharing below the file level, or is it just at, for example, can you say I want to share part of a file but not the whole file, or is it really sharing the lowest level of granularity for security and sharing is the file?
Yeah, the lowest level of granularity is the file, but you can actually lock at the subfile level, so you can have several processes maintaining locks at the subfile level. The only thing I'd caution against here is if you're looking to have sharing and performance, then you're really out of luck, because sharing stuff and locking doesn't actually fit with performance. We spend an awful lot of time in an awful lot of systems doing lots of locking that is completely unnecessary, and it reduces the performance, but we need to do it because, hey, if I'm updating your bank account and I don't lock those records, then, hey, somebody else updates them at the same time, we're in deep trouble. But the number of times that 2 people try and update the same bank record is a really, really, really small number. But we have to go through all the overhead. So, I'd advise that, sharing and locking and performance do not necessarily go together. In fact, they work against each other.
Yeah, great point, Alex. Actually, I think at the block level, if I were running a database on top of block storage, I might have locking at the record level, but that locking would be done not by the storage, but by the database application itself, and not within the storage protocol level. So let's answer, see if we can get to at least one question from the audience. So it's a use case application, and the question is, one could argue that file system is not really a good match for big data. Would you agree or disagree? Alex, and then Mark, if you could take that question. What about big data storage?
Big data to me represents any data at scale, and one of the issues you've got is, okay, so file systems may not be the best fit for analyzing data at scale. It might be object systems that are better at that, but 99.9999% repeating of your data exists in file systems right now, and if you want to analyze it, then hey, why go to the effort of moving it from one format to another? If it's out there in files, analyze it in files. I mean, it's really a no-brainer. I am not a big fan of copying, reformatting, and variously remunging data. Big data is big data, and if it happens to be in file format, process it that way.
Mark?
Yeah, and it's really when you want to get the data in the first place that object really makes sense, right? If you've got sensors all over, how are they getting that data back to the analytics software? And object allows a very simple device running over a cellular network to access the objects and send objects into the system that's going to analyze them.
Great point, Mark. Thank you. So I'm going to go ahead and let's wrap this up again. So first, people are asking about the slides. The slides are already available for download from the SNIA ESF website. Second, this webcast will be available as a replay through BrightTalk, and you can also find the link on the website. So if you want to see it again, if you want to see the slides, those are available through the SNIA website. We do have some more webcasts coming up. So the next live webcast is everything you want to know about storage, but we're too proud to ask. That's a long-running series, very popular series. This will be part Aqua and talking about storage controllers. And that is in about 4 weeks on May 15th. On demand, we have all the other everything you want to know, but we're too proud to ask webcasts. Again, on the SNIA website, go to the SNIA website, go to the ESF section, and look at the webcasts page. We do have other blogs and webcasts about file, block, and object storage on our website. They're here. And again, you can download these slides and get those links. And we would like to ask all of you to please rate this webcast before you leave. So please put in a rating, enter any comments you have. We always love to hear the feedback, good and bad. Of course, we like good feedback better, but if you have ways in how we could improve or topics that we didn't cover, please do write those as well in the feedback. As I mentioned, this slides will be posted as a PDF. Also, we will take all the questions. There are about another 7 or 8 good questions that we didn't get to. We will answer them all in a blog and post that online. You can follow us, including announcements about webcasts, and when we post these blogs on Twitter at SNIA ESF. So with that, I would like to thank everyone for attending. It's been great having you. Thank you for all the great questions. Again, I'm sorry we didn't answer them all, but we will answer them in written form in the blog. If we didn't, so your question is not wasted. Big thank you to Saqib, Alex, and Mark for presenting. Great job, everyone. And again, we're just a few minutes over the time limit, so we'll go ahead and wrap up the webcast. But we look forward to answering the rest of the questions and seeing you at the next SNIA ESF webcast on May 15th. Thank you, everyone.